substrate concentration. And let's say that that we start off with NADH and it is being oxidized, and therefore the metabolite is being reduced. It's a redox reaction. We can't have one without the other. So if we're monitoring the absorbance at 340 nanometers as a function of time, if we were to see a curved line, we would be frustrated because we would say, darn it, I need to redo this assay. I need to lower the enzyme concentration and redo the assay, because what I'm looking for is I want to see a linear decrease in the absorbance as a function of time. The reason why I want to see a linear decrease, and I mentioned this last time, if we use the Beer-Lambert law, so that the absorbance is equal to a molar extinction coefficient times the concentration times the path length. That's just the width of our cuvette. That's usually 1 centimeter, so we'll just kind of ignore that since it's 1. If we look for the decrease in absorbance as a function of time, so d absorbance dt, that would be simply equal to the molar extinction coefficient, which is a constant, times dc dt. And that's what we're interested in, change in concentration as a function of time. That is a rate. So that just tells us that if we bring over the molar extinction coefficient, then we have a rate. But we want it to be linear because we want to be in the realm of zero order kinetics. And let me explain what I mean by that. So if d a dt is equal to a rate constant times the concentration of A raised to the 0 power, that would be zero order kinetics. And so anything to the 0 is 1. So basically, I'm going to separate variables, and I'm going to have D, change in concentration of A, is equal to K dt. And then if we integrate, we have A is equal to K times T plus our constant of integration. And so then we just imagine, like, when the time is 0, so right at, before we have started the experiment, then the concentration of A will be whatever our initial concentration of A is. And therefore, so if we let T be 0, then A naught, our initial concentration of A, is seen to be equal to our concentration. So we could say A is equal to K times the KT plus initial concentration of A. And if this was a decrease, so since I'm doing a decrease up here, I'll go ahead and make this minus. I'll bring over the minus sign, and that just carries through. So then this equation is in the form of a straight line. Y is equal to X plus B. So our equation is in the form of a straight line, and that's what we're looking for. We want to see the decrease in the concentration of A. We want it to be linear. The y-intercept, as we saw, is that initial A concentration. And then the slope is seen to be minus K. That's our slope. So if this concentrate as a function of time, so if the change in concentration as a function of time is linear, then we know we're obeying zero order kinetics. And basically for D absorbance, dt, if we multiply it by 1 over the extinction coefficient, that gives us dc dt, which is the change in concentration as a function of time, which is what we want. So that's why we want it to be linear. So that's a little refresher on zero order kinetics. And then the next thing I want to do before we get back to our derivation of the Michaelis-Menten equation is to show you, this is from the first action center problem that we'll do tomorrow. It's a simple first order reaction. A goes to B. That process is governed by rate constant K1. And we're looking for a key phrase, elementary step. If we know that that happens by an elementary step, then we're assured that we can simply write the rate is equal to the rate constant times the concentration of A. Equivalently, we could say the rate, which would be minus dA dt, because dA dt is decreasing, so minus of minus will be positive. We want our rates to be positive. But minus dA dt is equal to dB dt, the formation of B as the function of time. They're equal to each other, and they're both expressions of the rate. So we can say minus dA dt is equal to K1 times the concentration of A. So there's that, K1 times the concentration of A. And I could pick either one of these, but I choose to keep the same variable. And so I'm going to use minus dA dt. If I bring over the minus sign to the other side, and we integrate both expressions, and then do some simplification, we get the concentration of A is equal to the initial concentration of A times E raised to the negative K1 times T. So I'm going to rewrite this equation a little bit differently here. A, to show that this could be the amount of A. It could be the number of A molecules. It could be a concentration. It could be just whatever amount we're thinking. So A is equal to A naught E, and then I'm going to write plus or minus KT. Now you might be asking yourself, well, over here in the derivation, we had E to the minus K1 times T. And here I'm hedging a little bit, and I'm saying E to the plus or minus KT. And the reason why is because this equation can serve double duty. It can work for exponential decay. That would be a decrease in A as a function of time. Or it can work, and then in which case we would use the minus KT. Or it can work for exponential growth, in which case we would use the A is equal to A naught times E raised to the positive KT. And it works in both cases. And there are many instances in biochemistry where we might be interested in the rate of growth of an exponentially growing population of, say, bacteria. If we are culturing E. coli and we want to have an estimate of how long it will take to saturate the culture, and we assume the bacteria doubles every 20 minutes, then we can work out how long to let our culture go before it is saturated. We might be doing an assay with a radioactive isotope, which will decay as a function of time, in which case we would use the A is equal to A naught E to the minus KT. So this equation turns out to be very powerful. I'm going to call it the simple exponential equation, and it's one I want you to know because it's going to come in handy, as you will see, as you will see quite often during the Action Center and on this week's homework problems. And I'll give you a quick example. Let's say that we're dealing with exponential decay. A is equal to A naught E to the minus KT, because we're told it's exponential decay. And I'm curious what T is when, so what is T when my concentration of A is half my initial concentration of A. So whatever amount of A naught that I start with, when that decreases to 1/2 A naught, so when that A is 1/2 A naught, I want to know what's going on. So I'm going to just substitute 1/2 A naught for A, and that's equal to A naught e to the minus K, and I'm going to put T subscript 1/2, because I'm interested in the half-life, how long it takes for half of that substance to decay. Well, A naught cancels. So that's the beauty, part of the beauty of this expression is it doesn't matter what the initial amount is. That goes away. If I take the natural log of both sides, I have the natural log of 0.5, which will be negative, and that's equal to minus K T 1/2. And then I can say, okay, well, the half-life, T 1/2, is the natural log of 0.5 over minus K. So the natural log of 0.5 will be negative over minus K. Negative over negative will be positive. We want our time to be positive. But if we know what K is, what that rate constant is, then we can figure out the half-life. And most of the problems that you're going to do, you either know K, and then you can figure out the half-life, or you know how much the substance we're thinking about has increased or decreased after a certain amount of time, in which case, like let's say in order for A naught to go to, say 1/10 of A naught, that takes 10 days, if we're told that. So now we know the time, and we can use that information to solve for the rate constant. So we can say 1/10 A naught is equal to A naught e to the minus K, and then our T is going to be 10 days. So I ran out of room, but I could write that number now if I wanted. The A naughts cancel. I could take the natural log of 1/10, and that's equal to minus KT, and then my K is equal to natural log of 1/10 over minus T, which would be 10 days. Once again, I have a natural log of something less than 1 is negative over something that's negative, that's going to be positive. So my rate constant will have units of reciprocal days, days to the minus 1. So for a first order rate constant, the units are always reciprocal time. In this case, because the time unit we were working with was days, our rate constant will have units of reciprocal days. So natural log of 0.1 over minus 10, and then whatever that number is per day will be our rate constant. So you'll have a lot of questions on the homework and on the Action Center that require you to either solve for the half-life or the T doubling. You could sometimes solve for the T doubling, in which case that would be natural log of 2 over K, and that would be the time that it takes for the population to double, assuming it's an exponentially growing population. So that turns out to be really powerful, and there are a lot of applications in biochemistry where we use that. The other concept I want to mention before we get back to the deriving the Michaelis-Menten equation is if we have some population at some initial amount, and then we let that population increase by some proportion x, so x times that initial amount, and then that is equal to the population size at some future time, then x, the proportion of increase, is seen to be p minus p naught over p naught, and that is x. That would be the proportion of increase in our population. So here's the example I like to give because the numbers are pretty easy. If something starts out and it's 10 units, and then after a period of time it is 20 units, what percent growth is that? a lot of people will just quickly divide 20 by 10 and say that's 2, therefore 200% growth, and that's wrong. You have to subtract that initial 10. So 20 minus 10 over 10 is going to be equal to 1. So that's 100% growth, which makes a lot of sense. We doubled. We went from 10 to 20. So we had 100% increase. But people often forget to subtract that initial amount. And so that's something I wanted to remind you of. And then so I think we're good to go. And now I'm going to get back to the Michaelis-Menten equation. We had started to write on the board last Thursday that a protein colliding with a ligand or ligand forms a protein-ligand complex. This is something we dealt with back in chapter 6 or 5, I think, 5. And that happens via rate constant K1 over rate constant little k2. I'm going to use 1 going left to right and k subscript even number going right to left. If I say this occurs by an elementary step, we can say that 2 things productively colliding, little k1 would have units of reciprocal concentration, typically per molar, but it doesn't have to be, and reciprocal time, typically per second, but as you saw a minute ago, it doesn't have to be seconds. It could be per minute, per hour, per day, whatever unit is convenient to work with. And then for K2, we're thinking about one thing breaking apart. So it is a unimolecular process, and so the units are just reciprocal time, often reciprocal seconds. So far, so good. And then also, I guess while we're at it, Kd, the dissociation constant, if you recall, we did this on the board a few weeks ago. That's little k2 over little k1, and it is equal to the concentration of free protein at equilibrium times the concentration of ligand at equilibrium over the concentration of the protein ligand complex at equilibrium. And then, so what we had done is we're trying to make parallels with that. And so our macromolecule is going to be the enzyme. Instead of a ligand, we're going to call it a substrate. But nonetheless, they have to productively collide via rate constant K1 to make the complex ES, which can dissociate via rate constant K2. And so far, the parallels are exact. But because it's an enzyme, we can have a catalytic step. This would be rate constant K3, and that would involve the catalysis where the substrate is converted.
He's so cute.
The substrate is converted into the product. So up until the point where we form PL and ES, it's the same, but then it becomes different because the enzyme substrate complex can, other than just dissociating, which it can do, it can also go on and regenerate the free enzyme and have chemical reaction occur where the substrate is converted into the product. And that's going to make a big difference. Notice how for K1 and K2, I used the equilibrium arrows, but for K3, I used a unidirectional arrow. And what I want to say is why we do that. It's kind of the advantage that the experimentalist has. We can control conditions. So during the early time course of the reaction, when I have a lot of substrate and no product, we're going to make the ES complex. It can dissociate, but then it can also go on and make product. But there is going to be so little product relative to the amount of substrate during the early time course of the reaction that the chance of a product binding with the enzyme and making the having catalysis and making the ES complex is very minimal. So this approximation is only valid during the early time course of the reaction. Otherwise, we would have to have a unidirectional arrow, call it K subscript 3, and equilibrium arrow, and then an equilibrium arrow going backwards, call that K subscript 4, and that would be for E plus P, productively colliding. We're kind of wrapping catalysis and collision in one step and making ES and then going backwards. So we technically do have all this, but we're saying during the early time course of the reaction, we're predominantly going left to right. So we're ignoring the K4 step. And that turns out to be a reasonable approximation, especially during the early time course of the reaction. So we want a rate equation. We want to have the velocity. Some people will write V naught for the initial velocity. And if you think about the step that governs the formation of product, that's going to be K3, rate constant K3, times the concentration of ES. So if we knew what the concentration of ES was, and we knew what K3 was, we could multiply them, and that would be the step that governs the rate of product formation. So our goal now shifts to trying to find an expression for the concentration of the enzyme substrate complex in terms of variables that we can know and have a better handle on. The reason I don't know what ES is because I start with free enzyme, I start with the substrate, I add as soon as I add the substrate or as soon as I add the enzyme, they start colliding and making this. This can break down, this can go forward. At any point, I don't know what the enzyme substrate complex is. So we're looking for an alternative expression for that. And before I move on, what would be KD for the ES complex? Wouldn't it just simply be K2 over K1, just like it was K2 over K1 here? And that would be concentration of E, concentration of S over the concentration of ES. So it is the dissociation constant for the protein ligand complex is entirely analogous to the dissociation constant of the enzyme substrate complex. It's just little K2 over little K1, concentrations of the free enzyme, concentration of the free substrate over the concentration of the complex that we're starting with. That's important. We're gonna come back to that idea in a minute. But for now, we want to find an alternative expression for ES. So we're gonna play a little, because once we do, then all we have to do is multiply K3 by that, and then we will have our rate equation. So I'm gonna proceed analogously to what we did in the case of the protein binding to ligand. We said Y is equal to the fractional saturation, so PL over the total protein, and the total protein was either the free protein or the bound protein. So we're doing something analogous to that. I'm going to say ES over the total enzyme concentration. That's equal to ES over free enzyme, because so total enzyme is either the free enzyme or the enzyme substrate complex. So it's the sum of the two. So E total is equal to free enzyme plus bound enzyme. And so we're trying to get this by itself. So I'm going to bring ET over to the other side. So I've got ES by itself, but the problem is I still have ES on the right-hand side. So I'm going to try a little bit of algebra and multiply the numerator and the denominator by 1 over ES, concentration of ES. Effectively, I'm multiplying by 1, so I'm not really changing anything. And so what I get is ES is equal to E total, because I have ES times 1 over ES, that cancels, that's 1. And then I have E over ES And then I have ES times 1 over ES, and that's just 1. So I'm almost there, but not quite. I have ES by itself on the left-hand side, and I still have an ES term, but I only have it in one place on the right-hand side. So I need an alternative expression for E over ES. To come up with that alternative expression, I'm going to invoke what is called the steady state assumption. And so the steady state assumption is that there's a period early on in the enzyme catalyzed reaction where the concentration of the enzyme substrate complex as a function of time doesn't change. It is equal to 0. In other words, the slope of that line is equal to 0. Now, we saw this last Thursday when we were monitoring concentration of different species as a function of time. And we saw that ES increased, so this would be the concentration of ES. Initially, there wasn't any enzyme substrate complex, but as soon as we added substrate, we started making the ES complex. So it increased, and then it held steady. And then E decreased and held steady. So this would be the concentration of free enzyme, because initially all the enzyme was free. We hadn't added substrate yet. As soon as we add substrate, the free enzyme concentration decreases because the enzyme substrate complex is increasing. We call this realm the pre-steady state. And we call this realm the steady state realm. This is the sweet spot. This is where we want to be doing our assays, because the slope of our line is effectively 0. And so let me show you why that's so helpful. So if DES dt is equal to 0, then I can think about what forms ES. So let me rewrite our kinetic mechanism. E plus S goes to ES, ES goes to E plus P, little k1, little k2, little k3. So what forms ES would be k1 times E times S and what breaks down ES would be k2 times ES, that would break it down, or k3 times ES, that would break it down. That would decrease ES. So this would be the rate of formation minus the rate of breakdown. So minus k2 times ES minus k3 times ES. Kind of ran out of room. But the rate of formation minus the rate of breakdown, and that whole thing is equal to 0, according to the steady state assumption. And this is where the slope of our line is flat. So what I'm going to do now is I'm going to add these two terms over to the other side where the 0 is. So I have k1 times E times S is equal to minus, I'm going to factor out ES because ES will be common. This is going to be positive, sorry, because I added it to the other side. So K2 plus K3 times ET, or ES, excuse me. I factored out ES because I had, when I add this to the other side, I have plus K2 times ES. When I add this to the other side, I have plus K3 times ES. So I just factored out ES and I have this. So now what I'm going to do is I'm going to divide both sides by ES. That'll get rid of it on the right-hand side. I will divide both sides by K1 and S. That'll get rid of K1 and S on the left-hand side. Aha, I have E over ES, which is, if you recall, that's what I was looking for, an alternative expression for E over ES. I have it. It is equal to K2 plus K3 over K1, and I'm going to write it a little bit differently, times 1 over S. The reason I wrote it like this is because I have a constant plus a constant divided by a constant. I can call this whole thing a constant. So I have E over ES is equal to capital K subscript M, which is equal to K2 plus K3 over K1. This whole thing is equal to Km, and it's over S. So I am now going to go back to my rate equation, and I'm going to substitute Km over S, concentration of S, wherever I see E, or the one place I had E over ES. So let me rewrite that. So I have ES, we're trying to get it by itself. And we have ET over E over ES plus 1. I'm going to sub in Km over S for E over ES because they equal each other. So I have ES is equal to E total over Km times S plus 1. So I'm going to multiply I'm going to multiply the numerator and the denominator by S to clean it up a little bit. So I have ES is equal to E total times S, Km over S times S, the S is canceled, so just Km, 1 times S is S, Km plus S. So that's it. I said back here that if I could come up with an alternative expression for ES, all I have to do is multiply it by K3, and I have my rate equation. So that's what I'm going to do now. I'm going to multiply this by K3, and then I have my rate equation. So V is equal to K3 times E total times S over Km plus S. And just so you know, we go back to our kinetic equation. This was the catalytic step. It also included product release. So K3 is where S was converted to P and then released. So sometimes people will use, instead of K3, they'll use lowercase k subscript cat for the catalytic rate constant. So you should know that little K3 in this Michaelis-Menten kinetic mechanism is equal to little k cat they equal each other. They're synonyms. So alternatively, I could say, instead of K3 E total, I could say K cat E total times S over Km plus S. And then what we like to do in enzyme kinetics is ask ask some what if scenarios. What if the concentration of S is approaching infinity? In other words, the enzyme is just so saturated, it's going as fast as it can. So wouldn't something that is huge, when added to something in that limit, the denominator would approximately just be S, because S would be so much bigger compared to Km. So in that limit, I would have K cat times E total times S over S. These would cancel, and my velocity in that case would be K cat times E total. That would be as fast as I could go. And so people will call K cat times E total, they'll call that Vmax, the maximum velocity, as fast as you can go. When the enzyme is completely saturated because the substrate concentration is so high that in the denominator of our rate equation, we say something small added to something that approaches infinity is basically the thing that approaches infinity. Km is negligible. So in that case, in that limit, the concentration of substrate cancels, and we have little v is equal to K3 E total in that limit, and people call, or K cat E total or K3 E total, and people will call that Vmax. So that's one limiting scenario. So I'm going to rewrite that over here. We have little v is equal to K cat times E total or K3 times E total, which we're going to call Vmax times the concentration of substrate over Km plus the concentration of substrate. This is the Michaelis-Menten equation. This is something that you have to have implanted into your personal hard drives. It will come up again and again and again. And one thing I want to point out before we do the other the other limiting scenario is that this equation describes a hyperbola. Just like when we saw that the fractional saturation Y, we found that that was equal to the ligand concentration over Kd plus the ligand concentration. That described hyperbolic saturation. This Michaelis-Menten equation, we have this Vmax term, but we have a concentration over a constant plus a concentration that has the same form as our binding equation. So not surprisingly, that describes a hyperbola. So if we plot V or V naught as a function of substrate concentration for an enzyme that obeys Michaelis-Menten kinetics, it's going to appear hyperbolic. I hear my phone ringing. That might be OU calling. So I'll have to see what that is later. But anyway, this asymptote that we approach is that maximum velocity. We never quite get there, but the asymptote that we approach is our Vmax. So we have an explanation for why we have hyperbolic binding of a ligand to a macromolecule, and we have hyperbolic activity, velocity as a function of substrate concentration for an enzyme that obeys Michaelis-Menten kinetics. Okay, and so let me rewrite the Michaelis-Menten equation. You're going to probably write it so many times that you can't help yourself, you'll just know it. So little v is equal to Vmax times S over Km plus S. The other limiting scenario is, let the substrate concentration approach 0. So in that limiting case, then S, concentration of S in the denominator, is negligible, because it's approaching 0, negligible compared to Km. So in this limiting case, I can't emphasize enough, it's a limiting case, we have V is equal to V max times S, simply over Km. Because we said S was approaching 0, so it was negligible in comparison to Km. So now we have a constant over a constant. Vmax is a constant provided we stick with the same enzyme concentration. So in that sense, it's a constant over a constant times the substrate concentration. Aha, that kind of looks like K prime times S, which would be a pseudo first order rate constant. Pseudo first order rate constant. A constant over a constant is a constant, so a constant times the substrate concentration reminds us of a first order constant, and so we would call V over K. People, instead of saying Vmax over Km, people just say V over K is our pseudo first order rate constant. Another way of looking at the same thing is to define Vmax. So I'm going to do that. I'll do that here. So I'm going to say little v is equal to K cat times E total, because Vmax is K cat times E total times S over Km. And then we say, well, when the substrate concentration is approaching 0, all of our enzyme is basically free enzyme, because the enzyme's diffusing around waiting to collide with an S, but there's hardly any S because the concentration of S is approaching 0. So I can rewrite this as, in this limit, this is a limiting case, little v is equal to K cat over Km times E, because we're saying when the S is close to 0, all of the enzyme is basically free enzyme, times S. So now we have a constant times a concentration times another concentration. So people will refer to K cat over Km as a pseudo second order rate constant, because it's a constant times the concentration of two things that need to collide. So it's a pseudo second order rate constant. And it has units of per molar per time per second, typically. It doesn't have to be, but that's usually what the units are. So we have two different limiting cases. We let the substrate concentration approach infinity. In that instance, Km was negligible in comparison to S. So then the S is canceled, and we were left with V is equal to a constant, K cat times E total times, that. And so we called K cat times E total V max. The other limiting case was we let concentration of S approach 0. Then S was negligible in comparison to Km. And so then we had little v is equal to V over K times S, which we called a pseudo first order rate constant. Or if we go ahead and define Vmax, it's K cat times E total times S over Km. We said when the substrate concentration is approaching 0, all of the enzyme is effectively free enzyme. So then we have little v is equal to K cat over Km times E times S. So we called K cat over Km a pseudo second order rate constant. And we might be interested in, like, what is the maximum that we can expect for K cat over Km? So let's go rewrite.
Oh my God, bro.
Michaelis-Menten mechanism, E plus S. and you'll probably write this so many times you won't be able to help it, you'll just know it. Okay, so that's the Michaelis-Menten kinetic mechanism. And I'm interested in Kcat over Km. What is its maximum value? Well, Kcat, as we saw, is K3. Km, as we saw, is K2 plus K3 over K1. And then I'm going to say, if we have a really good enzyme, then K3 should be much greater than K2. In other words, E collides with S, we make the ES complex, and it far more frequently goes on to make product via rate constant K3, then it dissociates via rate constant K2. So in the limit, as K3 is much, much bigger than K2, in that limiting case, Kcat over Km is K3, K2 is negligible in comparison to K3 because it's so small. So in that limit, K3 over K1, which simplifies to just K1, because we have 1 over K1 is just K1. So in the limit where K2 is K3 is much greater than K2, Kcat over Km is going to be K1. Well, what is K1? K1 is this rate constant. That is the rate constant that governs the collision of two things in solution, one big, an enzyme, one small, a substrate. They're diffusing and they make a complex. They productively make a complex that goes on and make product. That is set by Mother Nature to be 10 to the 8th to 10 to the 9th per molar per second. That's as fast as two things can diffuse. A big thing and a small thing can diffuse in solution and productively collide. 10 to the 8th, 10 to the 9th per molar per second. So if we see an enzyme that has Kcat over Km in the ballpark of 10 to the 8th to 10 to the 9th per molar per second, we say that is a catalytically perfect enzyme because it's going as fast as diffusion will let it go. It can no longer be optimized any further because the limit on K1, which is what Kcat over Km approaches, is 10 to the 8th to 10 to the 9th per molar per second. So if we have a Kcat over Km value that's in that range, then we say, hey, Mother Nature has optimized that enzyme as well as she can. So with that information, well, actually, let me do a few more things, then we'll get back to the slides. So I'm going to rewrite the Michaelis-Menten equation.
Oh my God, bro.
For the umpteenth time. And then I'm going to take the reciprocal of both sides. So I'm going to flip the left-hand side. I'm going to have 1 over V. And I have Km plus S over V max times S. All I did was I just took the reciprocal of both sides. So I have Km over a denominator plus S over a common denominator. So I'm going to rewrite it a little bit. I'm going to say 1 over V is equal to Km over V max times 1 over S plus S over V max times S. I'm going to cancel that. And so now I have 1 over V is equal to Km over V max times 1 over S plus 1 over V max. So by me starting with the Michaelis-Menten equation, taking the reciprocal of both sides, and then just kind of rewriting it, I now have an equation that is in the form of a straight line equation. 1 over V is analogous to Y. Km over V max is our slope. 1 over the substrate concentration is the concentration of our independent variable X, plus 1 over V max is our Y-intercept. So why on earth would we do that? Why would we manipulate the Michaelis-Menten equation so that it had the form of an equation that describes a straight line? The reason why is because, as I said earlier, the original Michaelis-Menten equation describes a hyperbola. Little v as a function of substrate concentration. Before the advent of sophisticated computers, we did not know how to analytically fit a nonlinear equation. We didn't have the tools to do that. And so it was very common at the time, this is the 1930s, they would take a nonlinear equation, manipulate it, in this case just taking the reciprocal of both sides, so that it had the form of an equation that described a straight line. So that now, if we plot 1 over little v as a function of 1 over s, then it should have the form of a straight line. Our slope was Km over V max, and our y-intercept was 1 over V max. So if you know the y-intercept and you know the slope, you can figure out V max and Km. And so this is what scientists did in the 1930s before we had, powerful computers. They would play this game, take a nonlinear equation like the Michaelis-Menten equation, manipulate it somehow so that it had the form of an equation that describes a straight line, and then get the estimates of the experimental parameters in that fashion. So we no longer, I'm going to talk about this more. The people who first did this, their last names were Lineweaver and Burke, and so this is called a Lineweaver-Burke plot. We nowadays no longer use a Lineweaver-Burke plot to get estimates of Vmax and Km. Instead, we can use powerful computers, even just desktop computers, and we do iterative fitting to the nonlinear equation, and we can get estimates of Vmax and Km that are much better than the estimates we would get if we did the double reciprocal. And I will explain why when we get back to the slides. So I think we've laid the foundation enough now. I'm going to get back to the slides. So let me stop this share. And we're going to go to the slides. And then you'll see we made a lot of progress. So we're going to continue from there. Oops. Okay, so this is pretty much everything we've already talked about. We've talked about these limiting cases. Yeah, so we already went through all this. I guess I did graphically. Somebody turn off, please mute. Is there we go. So if we have, when the concentration of S approaches 0, if I draw a tangent line to the velocity as a function of substrate concentration, that tangent line would be my slope. When the substrate constant is approaching zero, and we call Vmax over Km our pseudo first order rate constant. When the substrate concentration is approaching infinity, the velocity is approaching Vmax. So graphically, that's what it looks like on the Michaelis-Menten plot. And then I just introduced you to this idea of taking the reciprocal of each side and getting what's called the double reciprocal plot, and using that as a way to estimate kinetic parameters. One thing that I didn't say that I'll point out is the y-intercept is 1 over Vmax, the slope is Km over Vmax, and the x-intercept is minus 1 over Km. I forgot to mention that, whoops. So this is called a Lineweaver-Burke plot or a double reciprocal plot. And I mentioned that nowadays we should do nonlinear fitting to the untransformed Michaelis-Menten equation, which is a nonlinear equation, hyperbolic equation. And then this is a figure that shows why Lineweaver-Burke plots should not be used to estimate kinetic parameters. Oops. So notice that we have 1 over Vmax is our y-intercept. 1 over the initial velocity is the y-axis. 1 over S, concentration of S, is the x-axis. And we have all these points here that are kind of piled up close to each other. And these are precisely the points that were determined at high substrate concentration. Because when S is very big, 1 over S is very small. So these are the points where we have a lot of certainty, and they end up piled real close to each other. And then notice the error bars. The error bars are getting bigger and bigger and bigger, so that way out here, this is the point that would be the lowest substrate concentration, because 1 over the smallest number would be the biggest on the reciprocal plot. And this is the point, this is the data point that is at the lowest substrate concentration, and it has the most uncertainty, the biggest error. And it has too much sway in determining the equation for the best fit line. So that's why these Lineweaver-Burke plots are not good for getting estimates of Km and Vmax. We should just do modern iterative fitting to the linear equation. Okay, and then here is a table that shows some Km values in terms of molar concentration, some Kcat values in terms of reciprocal time, and then Kcat over Km, oops. Okay, Kcat over Km, you just take Kcat, divide by Km, and you get a Kcat over Km. And look here, acetylcholinesterase, 1.5 times 10 to the 8th per molar per second. That enzyme has reached catalytic perfection. Here's another one, fumarase. This is an enzyme from the citric acid cycle, 1.6 times 10 to the 8th. We would say that enzyme has reached catalytic perfection. So any of these enzymes that have Kcat over Km values in the ballpark of 10 to the 8th to 10 to the 9th per molar per second, we say they are catalytically perfect enzyme. The other question I asked down here, is there any physiological significance to the Km values? Yes, there is. Km is often a reasonable approximation of what the physiological concentrations of those metabolites are. It's not an absolute, it's just an observation. And it makes sense because that's where the enzyme has proportional control over the rate of the reaction. If the substrate concentration just changes just a little bit, gets a little bit bigger or a little bit smaller, the rate changes dramatically if you're operating in the realm of Km. So yes, it does have physiological significance. And so that just reminds me, I do want to escape out of here. Whoops. And then I want to share my screen again because I have another thing to talk about. Okay. So if I ask you what Km is, you could tell me it is a collection of rate constants. It is little k2 plus little k3 over little k1. You can think of it as, I'm going to rewrite the kinetic mechanism, the Michaelis-Menten kinetic mechanism. You can think of it as K2 plus K3 over K1. The two ways that the enzyme substrate complex breaks down, K2 and K3, over the one way that the enzyme substrate concentration is formed, K1. So that's one definition. To get a second definition of Km, we're going to rewrite the Michaelis-Menten equation. And we're going to say, let's let little v be equal to 1/2 V max. Okay, we're just going to see what happens. So I'm going to rewrite this equation, but instead of little v, I'm going to substitute 1/2 V max. So 1/2 V max is equal to V max times S over Km plus S. I have something times Vmax on the left. I have Vmax times something on the right, so that cancels. I'm going to bring the denominator over to the left-hand side. So I have 1/2 times the quantity Km plus S, and that's equal to S. I'm going to distribute. So I have 1/2 Km plus 1/2 S is equal to 2/2 S, which is just S. But you'll see why I did that. I'm going to subtract 1/2 S to the other side. So I have 1/2 Km is equal to 2/2 S, which is just S, minus 1/2 S, because I'm bringing this to the other side. So 2/2 minus 1/2 is 1/2. So 1/2 S is equal to 1/2 Km. And now my 1/2s cancel. So I can write Km is equal to the substrate concentration at which we observe 1/2 Vmax. So again, Km doesn't just equal the substrate concentration, it equals the substrate concentration at which we observe 1/2 Vmax. Let me show you what that means graphically. So here's our y-axis, here's our x-axis, little v or v naught, substrate concentration, and here's our asymptote that we approach, never quite get there, Vmax. And our Michaelis-Menten plot is hyperbolic. So if this is Vmax, about half of Vmax would be here. Try to cut it in half. So then I come down here, and this would be Km. Km would be the substrate concentration at which we observe 1/2 Vmax. So that's our second definition of Km. If I ask you what Km is, you could either say, you need to know both definitions, it's little k2 plus little k3 over little k1, which mathematically works out to be the substrate concentration at which we observe 1/2 Vmax velocity. So that's, I forgot to mention that, and I wanted to mention that. So I'm going to go back to the slides now. Okay. All right. And then here's an example of Kcat over Km. Now this is something you're familiar with. This is chymotrypsin with different substrates. So it's Kcat over Km if it was trying to cleave a peptide bond after glycine, and you know glycine side chain is just a hydrogen, and there's that big specificity pocket. So we're not properly occupying that specificity pocket, and so our Kcat over Km is horrible. If we put in valine, we get a little bit of improvement. Some leucine cousins, norvaline and norleucine, we get a little bit of improvement, but it's not until we put in phenylalanine that we get a significant increase in Kcat over Km. And we know that phenylalanine is one of the natural side chains that fits into that specificity pocket. So this gives us a nice illustration of how Kcat over Km is reflected in a real enzyme that we've already learned about. We've already learned about chymotrypsin, at least to some extent. And so Kcat is how fast can you go. It's the turnover number, like 100 per second. The enzyme can make 100 product molecules in 1 second. But then the other part of it is not just how fast can you go, but how little substrate do you need? You know, how small can Km be, and you can still bind it efficiently. And if you're getting into the ballpark of 10 to the 8th, 10 to the 9th, that's a perfect enzyme. Now, chymotrypsin hasn't done that, but we kind of don't expect it to, because it's binding typically to a big peptide. Its substrate is itself pretty dang big. So it needs to have kind of a little bit of a broad specificity. And in fact, we saw that chymotrypsin will catalyze the cleavage of ester bonds, not just amide bonds. Okay, so what I've been talking about is steady state kinetics. Some people have criticized steady state kinetics, and they say, well, it's kind of like a black box. Something comes in, and then we don't know what the pathway is through the black box, and then something comes out. And to some extent, that's true. You know, some people will say, well, we can never prove a kinetic mechanism, and that's true, but it's the best tool that we have. And so here's a quote by a person who, among enzymologists, was pretty famous. His name was W.W. Cleland. He said, there are many ways to study enzymes and their mechanisms, but kinetics, the study of rates, is one of the most informative, and it has the advantage of looking at the reaction being catalyzed while it occurs. As such, it must be the ultimate arbiter in any dispute over mechanism, and all postulated mechanisms must be consistent with the kinetics of the reaction. And so what we've been dealing with the Michaelis-Menten mechanism is an enzyme that just binds one substrate. E binds to S. Most enzymes, about 60%, involve two substrates and two products. So that's more complicated right off the bat. Prior to about 1963, the field of enzyme kinetics was kind of a mess. And so that person that I introduced you to on the previous slide, Cleland, he published a series of highly cited articles in which he proposed a new shorthand mechanism. And so we write the different enzyme forms left to right underneath the line, the horizontal line, and then we draw the substrates coming in when they do. So if we start with the free enzyme and then A binds before B, we make an EA complex, and then B binds after A has bound, we make an EAB complex. We have catalysis. Substrate A is converted into product P. Substrate B is converted into product Q. And then product P dissociates. We're left with an EQ complex. Finally, product Q dissociates, and we're back to the free enzyme. He called that mechanism ordered by, because it's ordered because A has to bind before B, P has to dissociate before Q, and bi because it's bimolecular, two substrates, and bimolecular, two products. So ordered by would be this kinetic mechanism in the Cleland shorthand nomenclature. This reaction would be called random bi. Bi because it's two substrates, A and B, By again, because it's two products, P and Q, but oops, this time, the order does not matter. The enzyme can bind A first, make an EA complex, and then bind B, make an EAB complex, or it can bind B first, make an EB complex, then bind A, make an EAB complex, either way. We have catalysis, A is converted to P, B is converted to Q, P can dissociate first, and then Q, or Q can dissociate first, and then P. So that is very descriptive of what happens. It's still two substrates, two products, but the order of binding and the order of release is immaterial, so it's random. Here is another mechanism that he called ping pong bye-bye. Now, he got a lot of grief for that because that's not a very technical sounding name, but it's kind of a fun name. And it kind of makes sense. Let me show you what's going on here. The enzyme binds to A. We have an EA complex. We have a catalytic event, and A is converted to P, and the enzyme E is perhaps modified, so we'll call it F, the modified form of the enzyme. P dissociates, so we're just left with F, the modified form of the enzyme. Now B comes on, we make an FB complex. B is our second substrate. We have catalysis again, so we have two catalytic events, two separate catalytic events. B is converted into product Q, Q dissociates, and F is converted back to E, and we're left with E. So he called this because something comes on, something comes off, something comes on, something comes off. For some reason that reminded him of ping pong, so he called this ping pong bye-bye, and I get a big kick out of that because that was the name he used in a technical journal article. Let me take a look at the time just a second. I see that I'm over time, so we'll stop here, and we will continue Thursday, hopefully in person. Let me stop this share here. So we will continue Thursday in person, hopefully. If not, we'll have to do this again via Zoom. But have a good rest of the day. I will see some of you at the Action Center tomorrow, again, either in person or virtually. And I'll post an announcement when I find out what's going to happen there. And we'll end because I went a few minutes over. All right, see ya.